Well, now that we've kind of felt our way around the periodic table, I'm going to talk a little bit about the information that's contained on the periodic table that will help us understand how these atoms are put together. So before we talk about the stuff on the periodic table, we're going to talk a little bit about the basic building blocks of atoms, and here they are. There's basically three of these, unless you're a nuclear physicist and you can just bash the living heck out of some of these particles and get even smaller particles, but that's pretty exotic. So anyways, we've got electrons, protons, and neutrons. Electrons are very small. They're found outside the nucleus of an atom, kind of orbiting around out there. It has a charge of -1 and a mass essentially of 0. Its mass is like 1/1837th of an atomic mass unit. So in comparison to a proton or a neutron, its mass is essentially negligible. So a proton, it's found in the nucleus down in the center there, and its charge is a +1 and the mass is 1 atomic mass unit. Neutrons, also found down in the nucleus, and their charge is 0 or neutral, and they have 1 atomic mass unit. So keep in mind that the neutron has 0 charge or no charge. I usually tell this joke in class, but I can't resist doing it for one of these narrated PowerPoint presentations, and it goes something like this. So a neutron went into a bar, sat down, had a few drinks, and when he was done, he said to the bartender, "What do I owe you?" The bartender said, "For you, no charge." And I had a link to a YouTube video that had a so if you like a proper drum roll and cymbal crash, then certainly follow that link. Okay, so back to serious chemistry here. I just kind of randomly picked an element from the periodic table. I picked potassium, partly just to beat that into our heads, because the potassium and K, the symbol doesn't immediately line up, and some of the element symbols are tougher to memorize, and this one comes from Latin, where in Latin it was called kalium. So the integer numbers, the counting numbers here, are called the atomic number, and the atomic number tells me the number of protons down in the nucleus. So this has 19 protons down in the nucleus, and it also tells me the number of electrons orbiting outside of the nucleus. So I would expect to find 19 electrons outside of the nucleus in a potassium atom. The lower number in this case is the atomic mass, and what it represents is a weighted average of all the available isotopes. So this average isn't a straight average of the isotopes where I just add the two numbers together and divide by 2. What I do is I have to look at the abundance as a fraction times the individual mass plus the fraction of any other isotope times its mass. It's kind of confusing. As long as you realize that it is a weighted average. Sometimes in class I share that one way of thinking about this is if DMAC instituted a new admission guidelines based on weight, where women had to weigh exactly 120 pounds in order to be admitted, and men had to weigh exactly 180 pounds to be admitted. And after they institute this, they find that the average DMAC student weighed 130 pounds. So we weighed everybody, we divided by the number of students, and found that it was 130 pounds. That would suggest that there were more women on campus because the average was kind of skewed towards that more abundant member of the DMAC community. But I don't think we'll ever do that. Okay, so potassium, I looked it up, and it looks like it has 2 major isotopes, and then a couple that are just like trace isotopes, very unstable. So essentially, 99.9 or better, 99.99, and even like another 9 after that percent were these 2 isotopes. So I'm going to ignore any trace isotopes for now.
and 93.26% of the potassium isotopes have a mass of 39, and only 6.73% of the isotopes have a mass of 41. So you can see that the average atomic mass that's reported on the table is greatly skewed towards the 39 isotope. So if there's only 2 isotopes of a particular element, you can kind of guess which one is most abundant by how close it is to the average reported mass. Okay, so let's talk a little bit about this. The mass number tells me about the number of mass-bearing particles, and those are only neutrons and protons, and we've accounted for the protons, so the lower atomic number in isotope notation. So we put the atomic number on the bottom, we put the mass number on the top, which is opposite of the way most periodic tables are constructed nowadays. So for potassium-39, it's got a mass of 39, it's got 19 protons, and I put that on the bottom. So there's some logic to how they go about, let's see if I can bring up my laser pointer again. So there is some logic to how we go about this. So it's got a mass of 39, it's got 19 protons. So if I just do a subtraction to get the difference in the mass-bearing particles, I get a 20 here. So it's just simple subtraction tells me that there are 20 neutrons. When I do the same for potassium-41, its mass is 41, it's got 19 protons, so when I take the difference I get 22, so there's 22 neutrons. It's the protons that give the identity to an element. So as long as any element or any atom has the same number of protons, it's going to be the same element. So in terms of identifying what isotopes are, they've got different masses, different mass numbers, but they've got the same atomic numbers. Another way of looking at it is that they've got the same number of protons, but different number of neutrons. Okay, so here's a set of sample problems here. I need to figure out how many protons, electrons, and neutrons there are in each of these isotopes here. And typically, we don't write the atomic number in when we are talking about isotopes. They just figure that everyone that's talking about isotopes must have a periodic table handy. So one of the first things I do is I fill in that bottom number, because that allows me to figure out the protons and electrons. And then with just a little simple subtraction, I can get the number of neutrons. So when I do this, I fill in the lower number, 6 for carbon, 42 for molybdenum, 92 for uranium, and 82 for lead. The 6 tells me there are 6 protons, 6 electrons, and then to get the neutrons, I've got to take the atomic number, or the atomic mass, and subtract the atomic number from that. So 14 minus 6 gives me the 8 neutrons. Similarly, for molybdenum, the atomic number tells me protons and electrons. To get the neutrons, I take my mass number, subtract my protons. That's going to give me 58 neutrons. And uranium works the same way. 92 protons, 92 electrons. 238 minus 92 gives me 146 neutrons. Lead, 82 protons, 82 electrons. 206 minus 82 gives me 124 neutrons. So pretty simple, pretty easy. I think most people could do this without a calculator even.